Hello everybody, I am a physics student and I've been trying to understand the NABLA operator in different coordinate systems, and I wasn't satisfied with the videos I found on YouTube. They felt unmotivated and very algebraically heavy. I simply didn't like the packaging. So I worked on it myself, and what I done is built upon the work or the explanations that I learned from eigenchris in tensor calculus and tensor algebra. This is basically just an example of that. So I would suggest that you have to know some tensor calculus to follow along. And I think the videos that he made are essentials for anybody who's trying to understand physics and math. It's just something you have to go through. And I think my explanation, which is probably somewhere in the book, it's not that I'm original or anything, it's neat. That's why I wanted to share it. So here's some of the things that you need to know before we start. So you need to know how to change bases. So you have some vector v, and it can be represented using e1, e2 with coordinates with components v1, v2, or you can use different bases, e1 squiggly line, e2 squiggly line, and you have different components in this case. Now you can represent a vector using this, like matrix multiplication, and one way to think about changing the bases is by inserting the identity and the identity I, and I can be broken down into f inverse. So these are two matrices, one and the other one is the inverse. And basically, the basis vectors multiplied by f gives you the new basis, and f inverse multiplied by the components give you the new components. And what we're going to be doing is more general because we're working with vector fields. So it's not just one vector, it's an entire vector field. But it's the same idea. You have a vector field f, and it can be represented, for example, in Cartesian ex, ey, ez with components fx, fy, fz, and fx, fy, fz are functions of x, y, and z, and you can represent the same vector field using bases e rho, e theta, e phi, with corresponding functions, which are functions of rho, theta, and phi. Something to keep in mind is when you're dealing with orthogonal matrices, the inverse of your matrix is the transpose. And we're going to observe this as we work through our problem today. So first of all, one way to define basis vectors are through the partial derivative of some position vector in the direction of that coordinate. So ex can be defined as partial r, partial x, and ey, partial r, partial y, and ez, partial r, partial z. And these are trivial because we're starting in the same, we're representing r using ex and ey and ez, so it comes out very naturally. But this is very useful when you are finding the basis vectors for some arbitrary coordinate system. So we first need to find the basis vectors for our space. So we're going to be doing the derivations for spherical coordinates, and I use theta as the angle with the x-axis and phi as the angle with the z-axis, and rho as the distance from the origin, is the radial direction. And you have the equations right here relating the variables, as you can see it. And again, we're going to be trying to find the basis vectors for spherical coordinates. So we take the position vector r, and we take the partial of that vector, the rate of change of that vector in the direction of rho. And you can work through the algebra yourself. You can see it right here. I wrote everything, almost everything. And you end up with partial r, partial rho as this. Now, we try to find the norm of this vector, and you can see, and it turned out to be 1. So we define the basis vector in the rho direction as just a partial derivative because it's already normalized. Then we do the same thing for the theta direction, so the partial derivative of r in the direction of theta, and you can work through the algebra yourself. You need to know some trig identities of the addition of angles, and you need to know these two limits, the limits for sine h over h as h goes to 0, and the limits of cosine h minus 1 over h as h goes to 0. And using these, you can solve, you can do everything, check through all the details, and you get to this right here. Now we check for the norm of this vector. So we have it right here. We check for its norm, and the norm turns out to be rho sine phi. So we want our basis vectors to be normalized. So we define the basis vector in the direction of theta as this partial derivative divided by rho sine phi, because we want it to be normalized. And we do the same thing for the phi direction. So you can go through the whole thing yourself, and you get to this right here, and we check for its norm, and you check for the norm, and the norm turns out to be rho. So to normalize, again, we divide by rho, so the basis vector in the direction of phi is 1 over rho partial r partial phi. So now we found the basis vectors. We defined the basis vectors for spherical coordinates. So what is the next step? Well, the next step is to find a way to relate those basis vectors. So again, you have your NABLA operator. It's a vector, and it can be represented in Cartesian coordinates, and the components of the vector are partial x, partial y, partial z. And we can find the matrix or the transformation relating the basis vectors in Cartesian coordinates to the basis vector in spherical coordinates. In this case, it's not the basis vectors, it's just the partial derivatives, and eventually we're gonna account for the normalization at the end. So you use the chain rule to relate the basis vectors. So partial r, partial x is, you follow the chain rule. I wrote everything, and you can break it down as a matrix multiplication, and you keep in mind covariant and countervariant. You have to be consistent as you work through the whole problem. And we do it for the basis vector. We did it right here. Let's now do it for the partial derivatives, the components. And again, you use the chain rule, just standard, normal, and you can break it down as a multiplication, a matrix multiplication, and you end up with this matrix. Now, these two matrices are almost the same. You have this, we call it the Jacobian matrix, this matrix of partial derivatives, And this right here, what we derived, is the transpose of the Jacobian matrix. And that's interesting. Why is it the transpose? Because you'd expect to find the inverse. Again, you look here, as we did in the beginning, we had F and F inverse. Now we have J transpose. It's because we are defining a transformation between orthogonal bases to orthogonal bases. The spherical coordinates the spherical bases that we have defined are orthogonal, and the Cartesian bases are orthogonal. So the transformation between them is an orthogonal matrix. So the inverse of the Jacobian is a Jacobian transpose. So we start like this, and we break it down. We take these equations that we found relating the bases and the components, and we write it down like this. So we have Jacobian transpose, and we're trying to figure out how to calculate this. So the first thing we need to do is to find the partial derivatives inside your matrix. And this is standard. You can do it yourself. I wrote them down. They're all correct. I checked. And these are partial rho, partial x, partial rho, partial y, and so on. Just in case you didn't see them. Okay. And these are also continuation for them. This is phi x, phi y, and phi z. So we have them all. So then you write Jacobian transpose, and just all the partial derivatives that we found, you plug them in, and you do matrix multiplication, and you end up with this monstrosity. But thankfully, this is where things start to simplify. So you can check for yourself. For example, you have x squared plus y squared plus z squared. This is basically rho squared divided by rho squared, so you end up with 1. So when you evaluate them all, I wrote everything down right here. It's a bit messy, but you can understand it. You eventually get to this matrix right here. It's very close to the identity, but not so much. There are some scaling vectors that we have to account for. So it's like this. So after that, this is the last step. We write this matrix where it needs to go. It's in the middle. And we evaluate, we multiply, and you can go through the algebra yourself. It's just algebra. And now we account for the scaling based on our definition. So partial r partial theta is going to be equal to e theta multiplied by rho sine phi. So all I did is basically plug them in, and you can evaluate and you eventually get down to this. Everything I think is written in detail, so you can check for everything, and it comes out to come like this, which is like the book, which is brilliant because it took me so long to get here. But I'm thankful because I understand it now, and it's really nice, especially when you represent it not just algebraically. You show the structure and what we're doing exactly. You can do the same work for cylindrical coordinates, and it's much easier. I did the hard one, and it comes out as you expect. So we have the NABLA operator, and we can do a lot of things with it. We can calculate the divergence of some vector field by taking the dot product with the NABLA operator, and we can calculate the curl of a vector field by taking the cross product with the NABLA operator. There's actually also another way to get to the divergence, which is through the original definition. So you say, what is the flux through some surface as the volume approaches zero? And you can do this for Cartesian, spherical, and cylindrical coordinates, and you get directly to divergence. And it's a bit tricky. There's so many pieces that are moving, but you can do it. And the surprising thing is it's the same thing. The divergence that you get by taking the dot product of the NABLA operator that we found this way with your vector field is the same as finding it through the definition, which should be, obviously it should be the case, but it's just interesting that you use completely two different ways to get to the same thing. I mean, that's math sometimes. I don't know. So yeah, I hope you learned something today, and I hope it was helpful, and I would probably upload a PDF in case something isn't clear, and you can probably just go through the notes without watching the video and you'll understand everything. So have a good day.